Projectile motion example 3. Here's my little diagram of the situation. We're assuming that the projection point is 40 meters above the ground. We're ignoring the height of the person. And once again, we're going to split the problem into components, the horizontal. So here's the basic idea. Draw the diagram, split your problem into horizontal and vertical components. So every problem starts the same. V sub x, S sub x, and t. V sub I, V sub f, a, which is negative 9.81 again, meters per second squared, s, and t. Alright, kind of like the last problem, we're going to take this vector, this 35 meters per second vector, and we're going to break it into its two components. It's v sub x and it's v sub y. And we're going to use sines and cosines to do that. This is a 50-degree angle right here. And you can complete the rectangles or the triangles. Use sines and cosines. I'll do that for you and get the answers. And the components then, using sines and cosines, the x component is 22.5 meters per second. I'll put that in the table or in the chart over here. 22.5 meters per second, which will not change throughout the problem. Vertically, though, the 26.8 will change as the problem goes on, meters per second. Alright, the other thing I didn't label in the diagram, well, actually what we're looking for is S sub x. S sub x is this distance along the ground, which will not be 40 meters. The vertical height is 40. Well, let me look at that 40 for a second. When you throw this from the location of the person at the top of the building, we're going to call that point A, way up here at the top, where the person is, kind of darkening that in. But the ball is going to land way down here on the ground. I'm going to call that point B. That's where my final location is. The person's head or the person's hand is point A. Point A to point B. Alright, once again, the ball travels horizontally, but vertically, well, it also travels, but the vertical displacement will be negative 40 when all is said and done, when the ball lands at that final spot. Negative 40 meters. It's going to fall vertically 40 meters. Yes, it will travel sideways as well and follow the parabolic path, but all we care about vertically is the negative 40. Once again, if you're looking at the three numbers in the vertical column there, we can figure out v sub f and the time of flight. And we can do v sub f from the fourth uniform acceleration equation again, and that is v sub f squared equals v sub I squared plus 2as. In this case, we got 20. Well, v sub f we don't know. V sub f squared equals 26.8 squared plus 2 times negative 9.8 times 40. So a little bit of math there, but v sub f will be a square root of a number, but it'll be plus or minus the square root, but I know I have to take the negative square root of my final answer here because the ball will be going in a negative direction when it lands. So let me do all the math on the calculator. As I was doing my calculus on the calculator, I noticed I didn't put the negative over here. This has to be a negative 40 in this last substitution for this to work out. So you're going to have the square root of a pretty big number, but the calculator always gives you the positive square root, but you got to remember to make it the negative 38.8, negative 38.8 meters per second, because the ball will be traveling downward when it lands. Well, that's not my final answer. I'm circling it because it's an important number. I have the important number circled, but that's the final vertical velocity with which the ball hits the ground. So now I'm going to use another equation to figure out the time of flight. I can use the first uniform acceleration equation. Let me do that on the next page. The first uniform acceleration equation works really well here, and that is v sub f equals v sub I plus at. V sub f was the negative 38.8 equals the 26.8 plus negative 9.8 times t. When you plug this all in, you get t equals 6.67 seconds. That's the time of flight. Now if I go back to my horizontal condition, that's v sub x equals s sub x over t. That t will be the same as it is in the other, for both columns, horizontal and vertical. And the horizontal velocity was 22.5 meters per second equals my horizontal displacement divided by the time, 6.67. So S sub x, the horizontal motion of the ball, will be 6.67 times 22.5. And that is 150 meters, which is quite a ways. Soccer field and a half. And now we need to find the impact speed with the ground. When the ball hits the ground at the end, it will be traveling in a direction something like this. And it's going to be traveling horizontally at that same speed the whole time. That was the 22.5 meters per second. And it's going to be traveling downward at the 38.8 meters per second when it impacts the ground. So the hypotenuse here, the final impact speed, I'm going to call that just v, but v squared equals 22.5 squared plus 38.8 squared, just Pythagorean theorem. I call it Pythagorizing the problem. The final velocity of impact as it's hitting the ground is 44.9 meters per second. And that is the answer to part C.